Afternoon, everyone, and welcome to today's Maths Boost session, which today will be on the topic of differentiation. I'm Helen, and I work in the outreach team, and I'm joined today with Dr Rhian Taylor, one of our lecturers in mathematics, and she's going to be running today's session. Hi, Rhian.
Hello.
You'll see her pop up in a second, or you probably can see her on the screen at the moment, actually. I'm shortly going to hand over to Rhian for the presentation, and during that you'll be given the opportunity to ask some questions. So if you want to ask questions, you can do so using the Q&A function on the right hand side of your screen, and you can choose to make your questions anonymous as well if you want. Just check the box if that's what you want to do, and then I can ask those questions to Rhian as we go, or at the end, whichever is best. We are almost ready to start, so before we do that, I'm just going to mention that I'm going to send a link in the chat at the end for a variety of different things, but one of them is for a monitoring form, and it's just because as part of our record keeping procedures in outreach in the University of Chester, we monitor all of our interactions through an online system, and so it would be really great if you would follow that link. So it's for the Higher Education Access Tracker, or HEAT for short. It'd be really great if you could follow that link just to input your details. It's absolutely not compulsory, but it does allow us to evaluate the effectiveness of what we're doing. So I'll pop that link in the chat just so you know what that is shortly, but I won't hold Rhian up any further. I'm going to hand over to Rhian now for our session.
Oh, perfect. Thank you for that. So for differentiation, I don't know if people are in year 12 or 13 at the moment. If you're in year 13, you're probably quite stressed with a lot of assessments going on at the moment, and this should be some nice revision. If you're in year 12, I want to give you a hint today at what you're going to meet in year 13. So it might look like some horrible things, but I just want to kind of introduce everything. So one of the things that you'll get is differentiating your trig functions. So if we have sine x and we differentiate that, then we'll get cos x. It's a nice derivative. If we've got cos x and differentiate that, then we get minus sine x. It's quite difficult to remember which ones are the positives and minuses. But if you list them out in a nice order, say sine, cos, minus cos, then you can just differentiate down that list and then integrate up that list. It's nice to remember that differentiate down. So that's if you write it by sine, cos, and then minus sine and minus cos in that order. Another really nice derivative that you'll meet in year 13 is the exponential function. From its definition, the derivative is the function itself. So it's the nicest thing to differentiate because e to the x just differentiates to e to the x. That's my favourite one. And then another thing that people don't really like is logarithms. So if you've come across your natural log before, your ln x, that differentiates to 1 over x. So I'm going to do some examples just using a mix of these. So whether you're in year 12 or 13, you should be able to do this one. So if we have y equals x squared plus sine x plus 1 over x plus 7 ln x, and we want to differentiate that. So we can just go term by term in this one. We'll differentiate our x squared, and we get 2x. If you can remember what your derivative of sine is. We can rewrite the 1 over x as x to the power of minus 1, and it's easier to differentiate it there using the power rule. And then the 7 ln x, we'll just leave that 7 at the front and differentiate our ln x. So all of that should differentiate to 2x. Sine differentiates to cos. X to the power minus 1 differentiates to minus x to the power of minus 2. And then the ln x differentiates to 1 over x. So 7 ln x will differentiate to 7 over x. We can tidy that up a bit with that power of minus 2. But there's nothing else that you need to do to it. You've got your marks from that point. So that was quite a long one. Another tricky one, we'll try and differentiate cos x plus 1 over the cube root of x plus e to the x. Everyone's favourite part in that is probably differentiating e to the x, which is just e to the x. If you remember from the start, cos x differentiates to minus sine x. And then I've just rewrote that 1 over the cube root of x as x to the power of minus 1/3. And then it's easier to differentiate it from there. So we just take that power down, times it at the front, and then take 1 off the power. So we get minus 4 over 3 as that power. And from that point, you've got your marks in the question. If you had to, say, graph the function, solve it for anything, if you wanted it to look a bit nicer, then you can rearrange that. And that power of minus 4 over 3 is the cube root of x to the power of 4. So that's a bit nicer if you have to solve it or do anything else with it. So I'll introduce you to 2 rules that you'll meet in year 13. The first one is the product rule, and then the second one is the quotient rule. Then I'll talk a little bit about second derivatives and how they can be useful. So first, our product rule. If we have y is 2 functions times together, we'll call one u and we'll call the other one v. Then to differentiate that, we have u times by dv by dx plus v times by du by dx. This is one of the formulas that you do have to remember, but we'll have a look at an example. So if we have y equals x squared minus x times by x to the 7 plus x cubed plus 7. We've got 2 functions times by each other in that. You can, in this one, if you wanted to, just expand all of that, differentiate it how you normally would, and you'll get the same answer. This is why I wanted to start with this one, because you can already do this without using product rule. But I'll show you how much nicer it is with product rule. So my first function I'll call u, and my second function I'll call v. In my formula, I just want to find du by dx and dv by dx. So that's just differentiating each of those. So if I differentiate du by dx, then x squared minus x goes to 2x minus 1. And then if I differentiate v to find dv by dx, I'll get a 7x to the 6 plus 3x squared, and then my constant of 7 will disappear. From that point, we've got absolutely everything that we need to just put it into the formula. So our formula being u dv by dx plus v du by dx, I'll sub in each of those. If you wanted to expand it, multiply it all out, simplify it, it does get a little bit nicer. But you can check with that one. If you didn't use the product rule, just multiply it all out from the start, and just make sure you get the same answer as that. So that's one way you don't have to use product rule. This one will be much easier with product rule, and you will have to use it here. So we've got our 2 functions again, u and v. So u in this case is x squared minus x, same again, and v is sine x. So if I differentiate both of them to find my du by dx and dv by dx, sine x differentiates to cos, and then I can just put it all into the formula. So u dv by dx plus v du by dx is probably easier to remember in your head as u dv plus v du. If we sub all of that in, then if you want, you can expand it, simplify it a little bit. I haven't with that one because you've got all your marks from that point. As long as you don't make any errors in your expansion or when you're simplifying it, that'll be perfect. The next one that I managed to look at involves a log. So I've got one nice function and then the logarithms that people usually don't like. So I'll call my first one u and second one v. So u is 3x cubed plus 7 and v is ln x. And I'll differentiate both of those. So if I differentiate u, I get 9x squared, and if I differentiate v, I get 1 over x. Again, just putting it into the formula, you should remember this formula by now. It looks quite messy, this one, and there's not too much that I can do to simplify it and make it look any nicer than that. But we've got 3x cubed plus 7 all over x plus 9x squared ln x. So that was just using our derivative of ln x is 1 over x, which is a nice one to remember. I think this is my last example on product rule. So I've used 2 functions there, and some people prefer to do this a slightly different way. So if you don't want to do u, v, du by dx, dv by dx, and then put it all into the formula, because this is one of the formulas that you don't get in your formula booklet, you can do it this way as well. So call one your first function and the other can be your second function. And the formula is basically the first function times by the derivative of the second function. And then we just have to add the second function times by the derivative of the first function. So that might be a bit easy to remember. So you can go straight in for that one. So I've done my first function, e to the x, times by the derivative of the second function. So cos x differentiates to minus sin x. And then I do the second function, which was cos x, times by the derivative of the first function, which is the same, e to the x differentiates to e to the x. And that was it for that one. To make it look a little bit nicer, I've just took out a common factor of e to the x there, and then we've just got cos x minus sin x in between. So that was some nice examples of how to use product rule. The other rule that we have looks slightly messier, and it's called quotient rule. And this is when we have 2 functions as quotient divided by each other. So it doesn't matter in this one which one you call u and which one you call v. So u has to be your top function and v has to be your bottom one. And then the formula for this, fortunately you get this one in your formula booklet. We have v times du by dx minus u times dv by dx all over v squared. So I'll show you a couple of examples of using this one. So first, u is my function on the numerator, x squared plus 7x plus 3. V is my function on the denominator, x squared plus 3. And then for the formula, I just need to find du by dx and dv by dx. So they're quite nice derivatives to calculate for each of those. And then all of this is just putting it into the formula. It does look quite messy, this one, and it's a little bit more work than the product rule. But if it's more work, it's worth more marks, so we don't mind. With this, I've tried to expand it all, make it look a little bit nicer. And you can go through and double check all of that one, but you should get to minus 7x squared plus 21 all over x squared plus 3 all squared. I've left that denominator all squared because it doesn't get any nicer if I expand that one and simplify it. The next one on quotient rule, just using a couple more functions here. So I've used sin x and e to the x. So my u has to be on the top, that's my sin x, and v on the bottom, e to the x. If you can remember what your derivative of sin x is, sin differentiates to cos. And the nicer one, the derivative of e to the x, is just e to the x again. And then our messy formula for this one, fortunately, you've got it in your formula booklet, so you don't have to memorise it. Sub everything into the formulas, and you can kind of rearrange, make it look a little bit nicer, simplify some things out. So in that one, I took out an e to the x from every term because that was common throughout all of it. And we've just got cos x minus sin x on the top and e to the x on the bottom. So they were my 2 horrible quotient rule ones. The next thing that I wanted to kind of introduce you to is using second derivatives. So first derivatives are really nice. If you've done all your year 12 differentiation, it's quite a nice topic. Second year changes quite a lot. So if we've got a function, f of x, we can see here we've got a maximum point there at the top and a minimum point there at the bottom. And we know that at these maximum and minimums, the gradient changes from being positive to negative. So at that point, the gradient must be 0. And then here, the gradient changes from being a negative gradient going down to a positive gradient going up. So at that point, the gradient must be 0. So this is just our first derivative, our dy by dx must be 0 at those 2 points. What I'm going to show you is how to use your second derivative to find which one's a maximum and a minimum. So if we want to solve any maximum and minimum points, we just let dy by dx equal 0 and then solve it for x. To determine which point is a maximum or minimum, we'll substitute the corresponding value of x into the second derivative. So that's d2y over dx squared. Then we've got two cases. So if d2y over dx squared is positive at this point, then that point is a minimum. At that point, the curve will be convex. And if the second derivative, d2y over dx squared, is negative at that point, then that point is a maximum and the curve is concave at that point. Another bit of terminology that you need is a point of inflection. So that's a point when the second derivative changes sign, so either going from concave to convex or convex to concave. But I wanted to show you this with an example, because that's a lot of theory. So all we want to do here is find the maximum and minimum points, and then maybe the point of inflection of this curve. When we've got all of those points, it'll be really easy to sketch the curve. So first of all, we'll find our first derivative and set that equal to 0. So that was 3x squared minus 12x plus 9. And if we set that equal to 0, we can solve it for x. I think that's quite a nice quadratic to solve. So if we put all of that in, we'll just get you two values, x is 1 and x is 3, which is quite nice. Now if we look at the second derivative then, so the second derivative is just differentiate that again. So the first time I differentiate it, I get 3x squared minus 12x plus 9. If I differentiate that, then I'll get 6x minus 12. So then I'll look at this second derivative. So my first case, I'm going to look at my two solutions. So the first one was x is 1. If I put that into 6x minus 12, then my second derivative is minus 6. And because that's negative, that means that that curve has a maximum point there. If we consider the other point, when x is 3, if I sub that into my second derivative, so 6 times 3 minus 12, the second derivative is positive, so then that curve has a minimum point at x equals 3. When we've done the maximum and minimum, we'll just have a look at the points of inflection as well. So that was where our second derivative changes sign. So at some point it got to be 0 in there. So if we set this second derivative equal to 0 and solve that, we get 2. Our value of x is 2. So we'll see if this is actually a point of inflection. So we just want to look at the second derivative before and after this point. So I'll consider the 2 points 1.9 and 2.1. So just slightly before and slightly after that x is 2. The first one, if we put in x, is 1.9. Our second derivative is minus 0.6, which is negative. And the second one, if x is 2.1, then our second derivative is 0.6, which is positive. So that's what we wanted. We've got our change of sign there. So therefore, that curve y has a point of inflection at x is 2. This should be much easier to sketch the curve then, because we know where our points are. So we have a maximum point when x is 1. You can just sub that in to find your coordinate for the y value as well. We have a point of inflection when x is 2. I'll sub that in to find the y value of 3 as well. And finally, a minimum point when x is 3. So if we sub that in, we'll get your y coordinate as well. And then looking at those 3 points, our maximum, point of inflection and minimum, it should be a nice one to graph the curve then. So hopefully that was a nice introduction, or a lot of revision if you're in year 13, a nice introduction to what is coming in the next year. But if anyone does have any questions, I'm happy to go back through anything.
Thanks for that, Rhian. That was really helpful, I'm sure, for the students. As someone who's not gone past GCSE maths, it was eye-opening to say the least. We have had one question from Adila, who said, can we expect these examples on an AS paper? I've got a mock tomorrow and I'm slightly anxious.
Oh, bless you. On an AS paper, I think the differentiation for AS is really nice. It's in A2 where it really steps up. So for differentiation on AS paper, you could probably expect a nice, like, power rules, nothing horrible that we've done today. So everything's got to be easier than that. So good luck, you'll be fine.
There you go. From the horse's mouth, there you go, you'll be fine. We've got a whole range of these sessions which people can book onto. So I will pop the link to that in the chat, and you can book on to follow the link to the next sessions as well. I'm also going to pop in the chat the link to the form that I mentioned. It has got a little pin for you there, so the pin's written there, so it's J9ZUT2. You can just copy and paste it from the chat. It will take you a matter of seconds to fill in the form, so it'd be great if you were able to do that. I'm just going to hand back to Rhian in case there's anything else that you want to mention or highlight. I know that the documents for this session are online as well, so I'll put the link for that in the chat too. But if there's anything else you wanted to mention, Rhian?
No, everything should be online then. So online, I've done like a student version of just the questions, no answers, if you wanted to go through it like a worksheet. I've got the full work solutions if you wanted to just look over what we've done today. I think the presentation might be up as well. Everything's there, and then soon there'll be a recording up as well if you wanted to go back over anything.
Absolutely. Yeah, everything that you've just said there, all 3 of those documents are all online. The link is in the chat now, so you can follow that link as well. We hope that you've enjoyed today's session, and we will see you all soon, hopefully. Take care, everyone.